In this video, we'll learn how to calculate the entropy change for an irreversible phase transition. In the last video, of course, we ended with a discussion of entropy changes for reversible phase transitions, those that occur at the transition temperature for which the two phases involved are in equilibrium. We start with the irreversible phase transition of liquid water to form ice at -5°C. We have a situation where we have supercooled the liquid water. And as I mentioned in class, you can find several YouTube videos where people actually show how they have supercooled a bottle of water down below its freezing point and essentially then freeze that liquid water almost instantaneously through a sudden disturbance. So, since we have an irreversible phase transition, clearly at -5°, the process is irreversible. What we need to do is devise a reversible path that would allow us to calculate the entropy change. So our path will involve first heating the liquid water to 0°C. We have reversible heating. Then taking that liquid water at 0°C and freezing it reversibly, since that would be the transition temperature at 1 atmosphere pressure. And then, after that reversible freezing, we will cool the solid ice that forms reversibly down to the -5°. So if we calculate the entropy change for each of these three steps, we will be able to then calculate the total entropy change by very simply adding the three together. So start with step 1, the reversible heating. We'll remember from our discussion of entropy changes that the entropy change ds is equal to dq over T, dq reversible over T. Since this is a constant pressure heating process, dq is just simply equal to the heat capacity Cp times dt. And when we go through and calculate delta S by doing the integration, we get a simple expression where delta S is equal to Cp natural log of T2 over T1. Of course, that is assuming that our heat capacity is independent of temperature, which is, for this very small 5-degree change, a very reasonable assumption. So all we need then are the heat capacity of the liquid water, which is undergoing the heating, and of course the two temperatures, T2 being 273 Kelvin, 0°C, and T1 being our initial temperature, -5°, which is 268 Kelvin. So we have the heat capacity of liquid water. Plugging the numbers, we get a value of 1.39 joules per Kelvin per mole, which of course is greater than 0, which is exactly what we would expect anytime we are heating something. We're going to see an increase in the entropy. Moving on to step 2, which is very simply the reversible phase change. We learned from our previous video that delta S for the reversible phase change is just equal to delta H transition over T on this particular circumstance. So in this case, we have delta S is equal to delta H over T. Delta H would be negative 6,008 joules per mole. Remembering, of course, and be careful about signs here, the enthalpy of fusion as listed in tables is, of course, a positive value. You need to recognize that since we're going from liquid to solid, this would be an exothermic process, so that should be negative. By the same token, we also will note that the resulting entropy change we calculate here is also negative. Because we're going from the liquid system to a solid system, we're going to a more ordered state. We would expect that to be negative in this particular circumstance. Moving on to step 3, which is very simply the cooling of ice back to the initial temperature 268. We use the same equation we used in step 1. The only difference is the temperatures are reversed, since the 268 is now the final temperature in the cooling process, and of course the heat capacity is going to be for solid ice as opposed to liquid water. So when we plug those in, we again get a negative entropy change, as we would expect for a cooling process. Remembering, of course, that for heating, we're going to get a positive entropy change. For cooling, we're going to get a negative entropy change. Now, therefore, to get the total entropy change for the system, we add each of these three steps together to get negative 21.3 joules per Kelvin per mole. Delta S is less than 0. And, of course, this might beg the question, naively, why does this happen spontaneously? Is this a violation of the second law of thermodynamics, which says that delta S should be greater than 0? And the answer to that question is no, it's not a violation, because delta S in the second law of thermodynamics applies to the entire universe. We've only considered the system. So what we need to do is then look at the entire universe, which means we need to look at the surroundings and calculate the entropy change of the surroundings to determine if this would be consistent with the second law of thermodynamics. Okay, so now we're going to talk about calculating the entropy change for the surroundings. You may recall from our earlier discussion that for the surroundings we don't have to consider reversible changes. We just simply calculate the entropy change based on the process as it actually occurs, be it reversible or irreversible. So in this case we have a phase transition, and the entropy change for the surroundings is just very simply equal to negative delta H for the system divided by T. Again, remembering that the reason for the negative is that the surroundings will have the opposite change in terms of Q as the system. When the system loses heat, the surroundings gain heat, and vice versa. So in this particular case, of course, we note the delta H system is negative delta H of fusion. It's an exothermic process, as we noted earlier. And so to calculate the process for the system, since we're going from liquid to solid, we very simply use the Kirchhoff's formula that because we know what delta H for this process is at 273 Kelvin, we can calculate 268 Kelvin as long as we are able to integrate this expression here, where delta Cp is going to correspond to the Cp of the solid minus the Cp of the liquid. And we are going to assume, again for this very small temperature range, that the heat capacities remain relatively constant so that we can pull them outside the integral when we do this process. So here we have our result for delta H at 268 Kelvin. We just simply need to know what delta H for the system is at 273, and as we mentioned earlier, it's exothermic, so it's negative 6,008 joules per mole. And then, of course, we need to know what delta Cp is, where delta Cp, again recall, is a Cp of the solid, which is 37.1, minus the Cp of the liquid, 75.3. So we get a negative change in the heat capacity. And then our temperature change, of course, is negative 5. So the overall delta H for the system at 268 is negative 5,820 joules per mole. Again, it's exothermic. Here we're calculating delta H for the system. Of course, to calculate delta H for the surroundings, we take the negative of that. So we take our number that we calculated earlier for the system, and then we take the negative sign of that, and that is going to allow us to calculate delta S for the surroundings, which is positive 21.7 joules per Kelvin per mole. Again, we would expect this, since we're dumping heat into the surroundings, we are going to expect that its entropy increases during this process. Now we can calculate delta S for the universe by taking the value for the system and adding it to the surroundings. So the system, of course, was negative, the surroundings was positive, and when we do the calculation we find that the overall delta S for the universe is greater than 0. It's not hugely greater than 0, but it doesn't matter. 0.40 is greater than 0, and that means that, according to the second law of thermodynamics, the irreversible freezing of water at negative 5 degrees Celsius will occur spontaneously. So we have, again, shown that we have no violation of the second law in this particular process. And again, the thing to remember is, when we interpret the second law, we must consider both the system and the surroundings before we can make any judgments. When we get to the next chapter and introduce the Gibbs function, we'll of course learn that the Gibbs function for constant pressure processes takes that into account in the calculation. So we won't need to explicitly consider the surroundings in our calculations. We have one more video that is going to be a short one associated with this chapter on entropy, and that deals with the third law. So stay tuned.